Yeah, start.
Okay. Hello, everyone, and welcome to the ARA user training webinar series. My name is Mohammed Salim, and I'm associate teaching professor in the electric and computer engineering department, and also a co-PI of the ARA project. So as you know, and based on the screen now, we have a webinar series. Actually, we started it last month with the ARA MIMO webinar. By the way, this webinar is now on our website with the recordings actually. So I will put the link into the chat so that if you want to check this one. And as you know, today's webinar, but I also want to let you know that in the next 2 months, we have two webinars. The first one is on April 24th, and this is actually the ARA-COTS 5G and experimental platform for programmable control of commercial 5G RAN. And the second one actually, and the last one of our series is on May 22nd, and this is actually the ARA Hall, a multimodal wireless X-Hall living lab for long-distance, high-capacity rural connectivity. So with that, I would like to introduce today's webinar, which is the AraSDR, end-to-end fully programmable wireless living lab for 5G and beyond. And today, actually, the presenter will be Josh Ofro Boating, and I want to introduce Josh actually very quick before giving the floor to him. So Josh is a PhD candidate in computer engineering department at Iowa State University, and I think we are going to celebrate soon for getting his PhD. And he is also affiliated to Wi-Fi Center. His research is mainly focused on democratizing 5G, 6G innovation through open source software stacks and software-defined radios, bridging the gap between indoor prototyping and large-scale deployment, right? The ARA platform. Also, his work spans between wireless living labs like ARA platform and also RAN sharing and virtualization frameworks. Also, he has published at ACM, Mobicom, and IEEE venues such as ICC and Melcom. He also earned multiple Best Paper awards. I think we will take like today's time actually to mention all of them, but he's having high quality publications, and also his broader interests include ORAN, enabling access to 5G, 6G innovation for rural broadband and precision agriculture. Without taking more time, I'm going to give the floor to Josh. Josh, if you can please start sharing. I'm going to stop my screen here.
Yeah, can you hear me?
Yes.
Right. Thank you so much, Professor Salim. I will share my screen here shortly, and then we can start. Can you see my screen now?
Yes.
Okay. So, yeah, my name is Joshua, and today I will be talking about the AraSDR, which is an end-to-end fully programmable wireless living lab for 5G and beyond. So this work is part of the ARA Wireless Living Lab, which is currently deployed in Iowa State University, and then its surrounding crop and livestock farms. So I'll take a moment to quickly go through the overview of this presentation. So first, I'll talk about ARA and why ARA is fundamentally different from other traditional wireless testbeds, what it is, and then introduce the AraSDR, present some couple of example experiments that can be enabled on ARA using AraSDR, and then I'll go through a live demo session, basically highlighting how new users can reserve compute resources, create containers, and then deploy their own end-to-end fully programmable 5G networks for their own prototyping and research. And then we'll talk about some enabled research and innovation on ARA, and then we end with some references for folks to check out later. So let's talk about ARA. So what is ARA? So basically, ARA is a large-scale platform for advanced wireless research. and it serves as a wireless living lab for smart and connected rural communities, enabling research and development of wireless technologies that provide affordable and high capacity communication for rural communities and then industries such as agriculture. So more importantly, I would like to emphasize the fact that ERA brings together researchers and academics and also industry and community stakeholders together to kind of like push the frontiers of 5G and 6G innovation. So that's kind of on the high level what ERA is. And why do we particularly deploy ERA in agriculture and rural settings, right? So um, this is motivated by the unique opportunities that the rural environment provides. Unlike urban environment, the rural offers rich and diverse use cases for 5G and beyond that scales from the extreme ends of the throughput and latency spectrum for applications requiring low throughput and high latency, and then also for applications requiring high throughput and low latency, and for anything in between this spectrum. And secondly, what is particularly important here is what we call the rural first advantage in piloting 5G and 6G applications, such as XR teleoperation, high resolution multispectral 3D imaging of plant and soil, and the fact that the rural setting provides us with the opportunity to easily prototype new wireless systems before they are actually deployed on complex urban environment or settings. So this in effect provides or presents ERA as a strategic advantage for 5G and 6G innovation. So I'll quickly go through the current ERA deployment. So this mesh presents the current deployment of ERA. So for the vertices, so the vertices basically represents the base stations that we have deployed and we are planning to deploy. So the green vertices that you see are the base stations that we deployed in the first phase. The yellow ones are the base stations we have deployed in the second phase. So in total, we have 7 base stations deployed. And then we also plan to deploy and currently ongoing deployment for 4 new base stations to complete the mesh. And then we have UEs that are deployed and distributed around this base station that are strategically located in areas like crop and livestock farms, research parks, and even airports. And I would also like to mention that we also currently provide coverage for the US largest farm progress show, which is going to be held this year in Boone, Iowa. So on the high level, this is how the ERA deployment looks like. I'll go into detail in the subsequent slides. But first, let me introduce some of the wireless platforms that we have on ERA that makes real world prototyping of 5G and then next generation of wireless or cellular communication possible. So first, we have the ERA RAN, which is our RAN platforms for high throughput commercial off-the-shelf and SDR systems. We operate or we provide opportunity for innovators to prototype in mid-band and millimeter wave frequencies, and also even for TV white space frequencies, which my colleague presented last month on ERA MIMO. We also have the ERA Hall, which is a multimodal long distance high throughput X-Hall platform spanning both terrestrial and non-terrestrial applications. But then within this ecosystem, we will be talking about AraSDR, which is the platform that provides us the opportunity to be able to prototype using open source 5G software stacks and also fully programmable hardware stacks as well. So let's talk about AraSDR. So why is AraSDR? What is the motivation towards AraSDR? So we deploy or design AraSDR based on the fundamental 5G challenge, right? The fact that 5G is largely operated in it's largely operated as commercial technology, right? Like it's more like proprietary, right? And this presents a couple of challenges. First, making it difficult or limiting innovation because researchers and developers cannot easily modify or develop new capabilities, right? And then, in effect, this raises the barrier to entry for folks in academia and researchers and even small industries or small network operators who cannot afford very expensive 5G software. But then the advent of open source 5G, such as Okudu, which was previously SRS RAN and then Open Air Interface, has provided us the opportunity to be able to lower the barrier to innovation, right? However, this open source prototyping using these software stacks also presents a very new challenge, right? Which we probably have come across, I mean, working with open source 5G. And then the challenge is real world fidelity, right? So you realize that most of testing and experimentation and prototyping using open source 5G are done indoors, right? On bench tops or tabletops in the lab, in a very controlled environment, right? Which really do not help to capture the real behavior of 5G in terms of propagation, interference, and mobility conditions, right? And then secondly, in terms of coverage, right? So in indoor settings, we have very limited coverage, and that's, of course, even though it helps us to prototype 5G on a small scale, but in terms of running it on a large scale, testing our algorithms to basically understand how they perform in a real world large scale environment, we kind of find that limitation lacking, that problem lacking. So now the question is, how do we move from a setup like this on our lab benches to a real world deployment, right? So that's where AraSDR comes in. So now I present AraSDR, which is an in-field open source 5G platform that maintains the end-to-end programmability from the UE to the GNOB and then the core. So on the high level, this is how the architecture looks like. So on the UE side, we have open source 5G stacks like OEI running the UE and then also even SRS run as well. And then we have platforms like the B210 software-defined radio. And even currently, we have commercial off-the-shelf radios that can be used as UEs. And to increase the coverage, we deploy amplifiers, which here we call the UE booster, right? So it has both the PA and an LNA in a single module. And then for the base station, we have software-defined radio base stations that are deployed. Currently, we have N320s, X410s, and X310s, and even B210s if that is what you plan to use. And then for the software stack, we still run Open Air Interface and then currently Okudu, right? And we have a similar setup there where we have the amplifiers, P and LNA to increase the coverage. And in terms of the core network, we also leverage these open source 5G core implementations from Open5GS, P5GC, and then SD core, kind of to provide a variety of options for folks depending on their use case or their research. So of course, this presents to be able to do something like this, it's you would have to solve a couple of challenges, right? For example, the synchronization between the software stack and then the hardware, which in this sense, the amplifier, right? How do we accurately synchronize the TDD slots transmission between the software stack and then the front end, which is the amplifier and then the antennas, right? So for detailed check of the various problems that we faced and then the new implementations that we did to make this working in the field, you can check out the papers that we have published so far on this work. So the AraSDR paper and then the AraRACH paper, which highlight some of the issues that we face with the random access procedure in the 5G. So for the deployment, we have AraSDR deployed across all the 7 base stations that we currently have on Era. So these are some of the pictures of the base stations on rooftops, on towers. So these are real world deployment or implementation of 5G, but available for researchers and developers, and also innovators to kind of build new 5G capabilities. For UEs, we planned initially for 54 UEs to be deployed around various residential, crop, and livestock um, um, settings, and even for city vehicles for mobility research, right? But currently we have 37 that are currently deployed. That's the green icons that you see. And then we have 17 UEs to be deployed and even more, right? These are some of the images of the UEs that we've deployed in the field, on green beans, in livestock farms, on tractors, on robots, even at the city water treatment plant to provide them with 5G connectivity for their surveillance purposes, and on the Iowa State University buses to provide students with internet connectivity, and also researchers with mobility experiment, right? So, and then city traffic lights, residential areas, and bioprocessing and biorefinery plants, kind of to give that residential setting for experiment, right? To be able to understand the behavior of 5G in industrial settings or industrial 5G. And then we have a couple of nodes or UEs that are deployed on robots in the field as well. We also have drone deployment as well. So now let's look at experiment. So how do we experiment on Era? How do we leverage this platform to do our research to build new 5G capabilities or solutions, right? So I'll first of all go through the experiment workflow for new users, and then I'll kind of take a quick glance at the user manual that we have, and then provide resources at the end of the presentation for folks who may want to kind of take a look and then register to run their research on Era. So first, a user will need to log in through the ERA portal. So we have a portal that you can log in with your university credentials as a student and even as a non-student, right? And then you have to reserve compute resources. So the compute resource reservation, we have, you have to, for an end-to-end experiment from the UE to the core, you have to reserve a compute resource for the UE. Here, an example compute resources on the horticulture UE site that we have. And then you also have to reserve a base station compute node to be able to run your experiment. And then finally, you also have to create a lease for the core network. We also have a centralized core network that is available for experimenters, depending on folks' preferences. There may be users who are only interested in running research on the run, right? So you could just like connect or get the N2 IP and then connect the Genome B to the already deployed core network you have, or even deploy your own core network. So after this, you create containers, right? So you have to get a container image to be able to create these containers. We have pre-created container images that you can leverage, or you can bring your own container image with your own installed packages for the experiment. So you create a container on the UE, and then on the Genome B, and then on the core network, right? So this is basically the monolithic setup. We also have the CUDU where you, depending on where you want to put the CU and then the DU, you can do that for your ORAN experiment. And then next you execute your experiment. So you have the experiment execution, and then you collect your data. And then after that, you have to delete the containers and then the resources, compute resources, to make them available for other experimenters to use. So you delete your UE container, you delete the UE, the Genome B, and then the core network, if you have created one. And then you start releasing the resources, the UE, the Genome B, the core network, and then finally you log out. So this is the experimental workflow. So we have a couple of example experiment ranging from transmitting and receiving and even visualizing 5G waveforms using UHD engineer radio, and then real world 5G prototyping with open source 5G software stacks like OEI or currently Okudu, which previously was SRS1. And we also have a couple of ORAN experiment that leverages ORAN compliant near real-time rigs like the Flex rig, and example X apps for folks who are new to Open RAN to use, and even for advanced researchers to build their own X apps and then test with the current setup we have. So I'll quickly run through an example like demonstration of how to reserve resources, create containers, run an end-to-end experiment. Here, I will use the SRS run outdoor setup or experiment, and then show how you are able to create your 5G network in the matter of minutes, right? So let me exit this presentation and then quickly look at. So before this, I actually want to show a couple of things, right? So this is the user manual, and this is one most important resource that I would suggest folks who are new to using Era to leverage, right? So we have information on what Era is, how to get started, how to register an account, how to reserve resources, and some example experiment, and even APIs that you can use or even create based on what is currently existing. So for this live demo, I want to show, so this is the live coverage of the Era deploy. Am I showing my screen? Okay. This is showing. Okay, yeah, this is what I wanted to show. So this is the live coverage map for Era. We have, as I already showed in the previous slides, right? So we have the base stations in the yellow icons here, and then we have the UEs deployed around the base stations. We also have a couple of mobile UEs, and then a satellite terminal here. But for this experiment, we will be looking at using the Gilbert base station we have here, and then one of the UEs around Gilbert, right? So depending on your experiment, you can actually get some feedback or information about the UEs and then the base station that you are using, right? The kind of radio technologies that are available. So for example, if I click on this UE, I can see the distance from the base station. And then I can also see the radio technologies that are available, B210. We also have the Skylark for massive MIMO experiment, and we also have a commercial off-the-shelf or 5G modems that you can use for 5G experiment. So here I'll be using this base station and then one of these UEs. So let's quickly start with, so you have to log in. So I'm assuming that you already have registered, and then you have the login details and you've been able to log in. So this is the landing page. Let me quickly, yeah. So you check the reservations, leases. So I already have created some leases here just to make the demo go a little bit faster. But if you want to create a lease, you first need to check the host calendar here to see nodes that has been already reserved or not, right? So it's kind of pretty open these days. So we have Curtis Farm Base Station and UE that are already reserved for some time, and then we have these Gilbert and then the horticulture UE that are reserved for this current purpose. So based on what are available, you can actually create a lease here, right? So you specify your lease name. You can leave this blank and it will give you a limit of 5 hours. Of course, you can request for longer hours based on your experiment, and then you create the lease. So I already have 2 leases created, one for the base station and then one for the UE. So next, as we saw in the experiment workflow, you have to create containers, right? So you go to the container session and then you create containers. So here, you specify the name of the container, let's say GNOD, and then the container image, right? So here we have predefined or pre created container images that you can use. You can also bring your own container images based on whatever experiment that you're working on. So I will use the SRS run GNOB container here, and then you have to specify the bash command to be able to have access to the terminal. And then you go to next, the host name, you can put anything here, maybe GNOB memory. You have to give enough memory to be able to run the software stack. So I think for SRS and OEI, I think 8 gig RAM or 4 gig RAM should be fine. For CPU, you can use like 8 CPUs or 4 CPUs. I'll use 8 here. And then you select the compute resource or the lease that you want to create the container on. So this is a base station container. So we create it on the Gilbert JNB lease. So we have a couple of base stations that you can use, but for this demo, we use the Gilbert base station. So we go to next, and then you choose the network to be able to have access to internet in case you want to install any packages in the container, and then you create the container. So whilst this is creating, so you see the status here creating, we can also create one for the UE. Right? So we have UE, and then you specify the UE image, whether your own image or you are using the custom Ara images, right? And then you go to next, you specify the host name, and then you you specify the memory as well, and then the CPU, and then the compute resource on which you are creating the container. So then you go to next, and then you select the network, and then you create the container. So now we have the GNOD container running, right? You have access to a console here that you can run your experiment in here, but mostly I advise that you check the overview of the container, get the floating IP address, and then you can SSH into the container instance and have access to you can create multiple terminals and have that flexibility of running an experiment instead of getting confined to the console here. So this is basically something that you can use for like a very quick experiment, but for very large project or experiments like building out the 5G network, you may want to um, kind of access the instance through SSH on your local computer. So here I'll create a SSH password to be able to have access to it, and then I'll just restart the SSH service, and I'll do same for the UE to also have access to the SSH terminal. So get the password, and then restart the SSH service. Okay, so now after doing this, I will pull up the my terminal, and then we can see how we can run these experiment here. So I have a lot of terminals here. So I'll just SSH into the base station. SSH. Okay. Oh, sorry. Okay, let me first get this. Uh, okay. And then we do a similar thing for the UE. So check, was that the UE or the base station? Let me quickly check. Okay, this was the UE. So we do a similar thing for the base station. So we pick the floating IP address, and then we can do the rest in the terminal. So SSH root. A bit slow here, but wait. Okay, yep. So okay, so I have two terminals for each of the instances, base station and UE. So here, I'm not creating a container for the core network because we have a central core network that's the base station connects to. And to be able to do that, we would want to, let me go back to the user manual here to show a couple of things. So this is the SRS1 experiment. So first, in order for us to be able to connect back to the core network, we have to check the bind IP on the GNode B that connects to the EMF and then the UPF on the core network, right? So for this experiment, we use the ETH4 interface for the N2 connectivity back to the core. So you would check it. Oh no, yeah. Okay, so that's on the GNode B. So on the GNode B, you have this IP address, and then we have scripts that are designed on each of these containers, right, to make it very easy to run the experiment. So it contains running the GNode B, the IP address of the software-defined radio. So for each base station, we have 3 software-defined radios, right, spanning 3 sectors of the base station at 120 degrees, right, azimuth, right? So depending on the location of the UE, you may have to select the software-defined radio or the sector that serves that particular UE. So if you go back to the user manual, we have pre-created command here. So here you basically specify the IP address of the software-defined radio, the bind address towards the core network, and then the gains of the TX and RS gains, depending on how far the UE is from the base station. So for this experiment, we have UEs almost a little over 1 mile. So you may want to increase the gains a little bit, play with the gains, and also the bandwidth, whether you want to do 40 megahertz or 20 megahertz. So let's go back here and run the base station. So as the base station is running, we also have similar scripts, which contains how we reset the UE to a clean state for the experiment, and then also how you can register to the network and then have like example commands to run ping and then IPERF, right? So and I would like to also iterate the fact that depending on whether or not you want to kind of view the GNode B and UE metrics in real time, you can specify this JSON metrics flag here, and then it will create a JSON file here, which contains the GNode B and the UE metrics, right? So you can actually tail in and check in real time the GNode B metrics, right? And then here we can also run the UE. Yep. So you can see on the base station, it starts populating the UE container, the PCI for the cell, the RNTI for the UE, the CQI, MCS, bitrate, and all that, right? So when you start the UE, so the script here, the script is available. So if you use the Era created containers, you can have access to the script and can modify it to suit your own requirement, right? So basically what it does is it resets the QuickTel radio to a clean state, and then it scans for the cells that are available and registers with the network, and then create a PDU session, and then provides you with commands that you can use to test the ping and then the IPERF, or even modify the command as you may deem or see fit. So it's rebooted. So now it's checking whether the UE is registered. So sometimes it takes a little bit longer to register. So it's yeah, so it retries, and now it's registered to the 5G NR cell, and then to start the PDU session, running the the QuickTel commands. And then after the session is done, the PDU session is established, it even gives you the ping. We kind of make it very easy for folks who are new to 5G. For advanced folks, you may want to do everything like manually, and then you can do that. You can also modify things as you want. So you can check the ping, you can just copy and paste it in the other terminal, and then check the ping for the link. And this is, once again, this is a 1.3 kilometer link, right? And you can also run hyperf if you want to check the capacity of the link. So this connects back to the network, and then you can see the throughput here as it keeps increasing. So as you see the throughputs here, you can also check the metrics, and you can also see that the downlink bit rates, it's changing for the GC metrics. And then, yeah, so basically that's like a very simple like 5G network that you just created on the Era platform. And then once again, this is a baseline. You can build upon it, modify things, change things around to suit your experiment. So you can stop this real-time checking of the metrics. Or if you want to do offline post-processing, oh, yeah, sorry. Yeah, if you want to do offline post-processing, you can just copy this G-Node B metrics JSON, and then you can check your metrics for the UEs that were connected to the network. Each one will have a unique RNTI, and then the other metrics as well. So after this, you stop base station, you exit, and then once again, you can just delete your containers, right? Just make so that you make it available for other users to also use if they want, right? So and just delete this. And yeah, that's basically an example demo of how to run a basic 5G experiment on Era. I will go back to the slides, just quickly run through this, and then if there are any questions, I can take that. So let me present this. Okay, so this is a live demo. So now let's look at some example research and innovation that can be enabled on Era. So first, some studies that we have performed so far on the platform. So multi-UE capacity and contention study. So in this study, we leverage this one of the base stations, specifically the Gilbert, and we have two UEs right here. So the focus is on these two UEs. So we have one that is line of sight from the base station, 1.2 kilometers distance, and then the other, which is in a valley, some sort of a valley, right, which is 1.3 kilometers from the base station. And then we check the throughput when both lanes are connected to the network, or both UEs are connected to the network, and then when you have a single UE and then the maximum throughput. So you could see some results here that are a little bit counterintuitive, right? So for the 1.3 kilometer UE, you expect that longer distances, you may have a little bit reduced throughput as compared to UEs that are closer, right? But then depending on the location of the UE, we realized that we had benefits from multipath and some sort of constructive interference that actually made the throughput a little bit better than the 1.2 kilometer UE, right? And then the same for the maximum throughput that we observed for each of the UEs, which was nearly 100 Mbps. And then the aggregate was a little bit more than what we observe in each one of the UEs. This results, once again, would not be able to be realized in a simulation environment, right, or an indoor environment, right? So this is the kind of research that ERA actually makes it possible in terms of even building new or designing new schedulers that can support a specific application depending on what results that you are seeing here, right? And then we also did some sort of like latency and reliability characterization, where we have the same two UEs, right? We look at the end-to-end latency for a single UE running independently, and when we have another UE connected to the same network, right? And then you could see that the round trip time for each UE increases when there's another UE contending for resources. Uh, Basically, based on the scheduler design, how much time it takes to process the packets, and then also even contention and then retransmissions, right? We see similar results with the jitter when we have the interfering node or the other node running or transmitting 64 bytes payload, right, or packets. And this is done using IPEF. We could see a similar results. And if you increase the payload size, you could see the jitter also gets worse, right? So this is particularly important for applications that require very reliable communication, very low latency applications as well, like teleoperation and then all that. So, and then last one that I also want to touch on is multi-cell interference research studies that we are kind of like looking at. There are also a couple of researchers that are also doing a similar research on ERA as well. So we consider one base station at um, the Curtis farm here, and then we have its UE here, and then we have the Wilson Hall base station as the interference cell. And then we also have a UE that is next to the other UE being served by the main cell, right? And then we check the throughput for the cell under test, which is the main cell, right? And you realize that obviously for interference scenarios, you see the throughput reducing drastically. Same for latency, and then jitter as well. And then finally for packet delivery rate, right? So in scenarios where we have like more interference, obviously you have a lot of like retransmissions and packets not being able to deliver um, to the network, right? And yeah, so I think these are some of the studies that are really interesting to look at in terms of how you design the run, how to even develop new solutions or algorithms that can make 5G behavior even tolerant to interference scenarios, right? And finally, I would like to talk about like how ERA enables open and AI run research, right? So for open run, we have a couple of experiments that uses um, the CUDU splits. We currently use open hardware, or programmable hardware like the software-defined radios. But then we are currently working on deploying like in the outdoor ORAN compliant ORUs as well. We have ORAN compliant near-real-time rigs that folks can use, develop their own XApps. In terms of AI run research, since data is particularly very important for AI, ERA provides that rich real-world data sets, which you can have the opportunity to create yourself. Closed loop experimentation where you can train your models, deploy and evaluate in the field, all on the distributed edge and cloud infrastructure that is available on ERA. So these are some of the references that I talked about in the presentation. The ERA portal, how you can create leases and experiments, containers as well. And then you have a user manual which contains all the step-by-step approach in creating, even from registration, creating leases and then running your end-to-end experiment, API references, contacts, user groups. We have Google groups for our users where they exchange information. If you have any problem, you can post it there. We also host office hours, and then for help and issue support, you can also leverage these um, email addresses as well. So this is where I will end today's presentation, and maybe I can take questions.
Thank you very much, Josh, for your very informative presentation and demo. And I think just for everyone, we are going to post the video for this webinar to our website. And now for questions, I see there are some questions already in the chat, but since they are not a lot of questions, may I give the opportunity to those wrote the question in the chat to unmute directly and ask the questions? I think if you can't unmute yourself, you just raise your hand and Ali will be able to unmute you. Okay, I think the unmuting process is not that easy here. So let me go with the questions in the chat. So I will start with Ali. Go ahead, please.
Yeah, I just want to say if anyone has any question, if you can raise your hand so I can unmute you.
Okay, let's give it a few seconds to see if any live questions are going to be here.
Here.
Hello, can you hear me?
Oh yeah, we can hear you.
Thank you so much for your great presentation. I had like bunches of questions, but maybe is it possible if you can share the slides again?
Oh yeah, sure. I can share the slides. Share my screen again. Yep.
If you go back to your first slides.
Okay.
I mean, yes, the one that you were showing the map, maybe we can start with that one.
Okay, yeah, sure. Yeah.
Exactly. So like you mentioned that you are using USRPs, but I didn't figure out like you're putting something to increase the power and how like your coverage is improved by that. And then you said that in one of your papers you have mentioned to do that, but I mean USRP itself, up to my knowledge, cannot cover more than, let's say, 10 to 15 meter, depending on how you have configured that in the lab. So what is the range of your coverage at the moment with all these improvements?
So yeah, of course, you're right. So USRPs don't really have like very high transmission power like the B210. I think like 1 or 2 dBm. So in the outdoor, what we have done is, if you look at this figure right here, we have interfaced the USRPs with power amplifiers and low noise amplifiers. So these amplifiers are 40 dBm transmit power, right? So we are able to right now we are able to increase the coverage from a few meters that we could achieve with the USRP to up to 1.3, no, even a little bit more than 1 mile. So I think in agronomy farm, we have been able to achieve a little over 1.6 kilometers connectivity with the USRPs, but then it has the amplifiers being integrated with them. So this is not just the USRPs here.
And with these amplifiers, you mentioned that you had synchronization issues, right?
Yes, yes.
Basically, you mean that the UE or the UE was not able to find the cell or something like that?
Yeah. So I'll touch on a few issues, right? So the first has to do with even modifying the source code for the software stack to be able to communicate with the to be able to communicate with the amplifier, right? So for TDD, right? So we have this uplink downlink switching, right? So during the transmission occasion, you should be able to accurately communicate to the amplifier to transmit, right? Because the amplifier is also TDD. So that kind of synchronization between when we transmit and when you receive, and even for mixed slots that has like uplink and downlink symbols within them, right? So you have to really do it on a very specific time to make sure that you don't miss the transmission. For example, I'll give an example, right? So in OpenAir interface, the way the messages, the random access messages are transmitted, right? So they are being transmitted, for example, in special slots by default, right? So you have uplink symbols and downlink symbols, right? So you want to make sure that the time that OEI is transmitting is the same time that the amplifier is also transmitting. Otherwise, you may have the problem of the messages not even going out of the antennas, right? So those are the kind of synchronization issues that I was talking about. And then also even the number of symbols that we use to transmit the messages, right? Those also affect the random access procedure, which we have elaborated in detail in these papers that I've provided the links.
I see. And is your code already open source? Can someone else also use that or not?
Yeah. So for my Docker containers, I have published them. The code itself, currently in talks with OpenAir Interface to add to their current commit version so that all folks who are using OpenAir Interface can have access to it. But then for right now, we are still like working on the IP issues to be able to get it committed to OEI. But then I have the Docker containers that I use for all these modifications. Yeah.
I mean, it is really interesting what you are doing, and I'm in direct contact with OAI people. So I'm really interested to see like when the code is open source and maybe someone else can also use that. If we have time, I will ask one more question, and then maybe others also have other questions. Like the test that you are doing with ping and iperf, like why do you think the results are reliable? Because as you know, like if you want to do really ping itself is not a good tool if you want to show that, you know, the packets, if the packet size is not controlled, if many other parameters are not controlled, then ping and iperf could not be, in my idea, the best approaches for showing a setup is working or not. And also you mentioned that you want to go like up to my knowledge, OAI is able to cover like 16 UEs up to now. And you mentioned that in your roadmap, you have higher number of UEs, right? What is the maximum number of the UEs that at the moment you can cover with this improvement that you have done?
So I haven't actually benchmarked the maximum number of UEs that I can connect to a base station. But then what I can say is that recently there was a work that I was doing that required like some aggregate throughput things that I was able to connect up to 6 UEs. But that, of course, that's not like I wasn't doing like any stress testing, but I was able to connect up to 6 UEs. I did not try adding even more UEs, but I think you should be able to add more UEs. I mean, I think this is based on the OEI code, to what extent, or to what maximum number of UEs that you can connect to the OEI code, right? So I think we should be able to get closer to that limit that currently OEI support, but then I haven't done any like stress tests to see what is the maximum that we can connect. But I think something that is interesting that we can look at. Yeah.
Okay, thank you. I tried to contact you after the webinar. Maybe we can discuss about the detail more. Thank you for your time.
Right.
Thank you, Arash, for your questions. Again, please, if you have questions, raise your hand and we'll unmute you and ask your question. We have around 6 minutes. We want to utilize them in live questions rather than just reading questions. Okay, I will, just to save time, I'll read the first question I have here. This talks based on lab-based or coming from business perspective from ground. As we had some experience earlier, 5G launching and deployment in the certain location, of course, commercially there, event until now still on B2C and some B2B for private network. Not sure, okay, maybe this is just like informing, and then I don't see other questions. other than what Arash already asked. So any other questions? Also, I wanted to let everyone know that the Era platform is open to everyone. So just like you can start using it immediately. So just going to our website and going to user manual and trying to look into how to create your account. And then, it's everything, all information actually is there. Hopefully it's easy to follow up. If it is not, you can contact us directly. Okay, my last call for any more questions. And feel free to write your question in the chat or raise your hand and we will unmute you.
Oh, I think there's a question here. Do
Yes.
you charge remote code programmable FPG? I'm not sure if I understand your question, but I don't know if you're also asking about whether you can program the FPGs on the software-defined radios. Yes. So we have a sandbox, indoor sandbox, and we have a couple of B210s that you may be able to have access to, and then we can work together, and then I mean, depending on what experiment that you are doing, right, make those changes to the FPGA. But I would like to also mention that we may want to also kind of like get involved in the experiment so that we are kind of like sure for any like issues that may arise in terms of like programming the FPGA, since the USRPs are a little bit expensive. But yes, to your question, like the simple answer is yes, we can do FPGA programming as well. So yeah.
Okay. Since we are almost there for top of our hour, the only thing I want everyone to remember is that we have our next webinars, which are on April 24th and May 22nd, which is around 1 month from today for the first one and 2 months from today for the second one. So please join us for those remaining webinars. And also, we are going to look for providing more webinars, and especially if you have a specific request or anything you would like us to present based on our test bed, please let us know. Send us an email with your request, and we will do our best actually to accommodate that request. Thank you, everyone, and we'll see you in upcoming webinars.